Welcome to part two of our lecture series from Wednesday, April 19th, where we look at the relationship between heat and work in two different types of chemical systems. So we're going to look at a closed system, which is kind of what we've been discussing up to this point, and then we'll compare that to an isolated system, which is honestly just a theoretical construct. There's no truly isolated system, but it's good to just kind of see the math work out anyway. So here on the board, you'll see that I have defined a closed system, which is what we're going to be looking at primarily in Chem 210 and even Chem 220. So a closed system is a system that can exchange internal energy through heat exchange or heat transfer or work being done or both with its surroundings. So we can have some kind of relationship between our system and our surroundings. Where we can have a transfer of energy out or in of our system, which is going to either be transferred to or from our surroundings. The only thing that we cannot transfer between system and surroundings in a closed system is matter. So for example, if I had something like let's say a sealed glass cylinder that contained some DI water, and as we'll talk about when we get to our gas laws and gas behavior, but you've probably already seen this just from, living in the world, some water vapor particles. Think about when you leave your water bottle in the back of your car for a minute, you'll see condensation, right? All of the water that is present in this system, if it is a closed system, will never be transferred into the surroundings. So all water molecules stay within the system. So this means that, again, the only means that we have of interacting with the surroundings, which includes, again, things like our beaker, and also just like the general everything that's not water, the surroundings, is by transferring our energy from our system through exchanging heat and exchanging work, and vice versa. Now, how is that different from an isolated system? So an isolated system is a closed system, but with a little bit more attached to it. So an isolated system exchanges neither energy nor matter with the surroundings. And again, you can imagine that this is something that's purely theoretical. There's no way that I could have a sealed closed system that contains what I call in my chemical system just my molecules that is not also interacting energetically, at least in some way, with the container itself, right? So it's a purely theoretical construct. But let's look at how the math would work out. So if our isolated system exchanges neither matter nor energy with its surroundings, then that means that the total amount of energy inside this system is constant. Meaning if I were to look at the change in total internal energy of the system, this would be equal to 0. Now, why are we talking about this and why do we care? So let's remind ourselves about how we calculate our total internal energy for a chemical system. So the change in the total internal energy of some kind of chemical system is the sum of heat and work, assuming that there's some change in heat and some change in work. So this is why it's okay to add this delta in here now. If we know that the isolated system is not going to be exchanging any kind of heat or work with the surroundings, then that means that if we're isolated, we are interconverting heat and work within the system. So it's no longer a transfer between system and surroundings, but rather this transformation, if you will, between the types of energy that is found in the system. And when you take your upper level physics classes, and even if you take a thermodynamics course for, like, let's say a Chem BS, you will talk about these isolated systems. There's a bunch of different ways we can kind of construct them. But let's think about what would need to happen mathematically if delta U was equal to 0. So I've got delta U, which is equal to the heat in my system and the amount of work that's in my system. And if this is equal to 0, then I could move over one of my variables and I get that heat and work are equal and opposite. So whatever I transfer away from heat, it's going to be turned into work absorbed by the system, and vice versa. I could also write it the other way. Let's do positive Q is negative work. So this is only in an isolated system. So isolated systems, this is where the change in the total internal energy of our system is equal to 0, which results in these relationships as long as these are all within the system. Okay. Again, we are going to be focusing in this class on closed systems. So we are going to be looking at changes between heat and work and interconversions between heat and work that exist between both a system and its surroundings. So let's talk then about how we might be able to calculate heat and calculate work so that we can kind of put this together into our total internal energy equation to see the relationships. So we're going to start with quantifying work, or figuring out how it is that we calculate what we called in our warm-up pressure volume work. So I'm going to start with a little bit of a mathematical derivation here. Bear with me. I think it's useful to see where these expressions come from, just because, you know, if I throw random math at you, then you don't really understand like what the math is saying. You don't understand like the language that the math is speaking. However, would I ever expect you to recreate any kind of mathematical derivation? Absolutely not. I'm just throwing it at you so that you see it in some kind of context and not just in a vacuum. So coming up, we're going to talk about how we can quantify work, our pressure volume work, in a chemical system.